have the main part of the group.
Enjoy grilling yourself. Today we pick one more from
done with work of Fatima. Let's briefly discuss it, and I will be very happy to do it myself. But if maybe next meetings, it is completely fine if we assign someone, so to say, not responsible, to advocate. If you advocate each other or persecute each other. Any changes or observed here? Is it looks better than last time? Anything can be improved?
It looks the same. It's just,
Huh?
It looks the same as last time.
No, it is so much better. There were like garbage atoms going up and down, and now they are removed. So it's very nice periodic structure. But what a reader may miss is what is the size of periodicity, because below this last atom, silicon atom, and above this last silicon atom, there is a kind of empty space, and one may put a box to show where the empty space ends or where this begins, or just put a bracket and tell what is the periodicity size. Because some non-responsible readers do not look into text, and if it is shown here, well, we don't care about readers, we care about reviewers. And then they will have no excuse to tell that they didn't understand it. More comments on the first figure? Anything about the second one? Figure itself or captions?
You said maybe for the right figure, or the non-radiative one, maybe make the transitions dotted, or not a solid line, just so it doesn't blend in
Okay.
with the band structure.
Either transitions dotted or the dispersion curve dotted, right? Okay. What do you think about this K2 to K2 and K2 to K3?
I get it by looking at it.
Huh?
I get it by looking at it. I understand
Okay,
it from
but
just looking at it.
it looks like not too general. One can tell delta K equals 0 and delta K not equals 0 to pretend that we are so universal. Okay. Were there any comments about verbal explanations what are radiative and non-radiative transitions? So everyone is happy with the language. Language, not like English, but logical explanation. Little bit weird.
It's a little ambiguous.
Yes. So one can add nothing wrong, but it lacks specifics. So if we are telling it is radiative, right here, right? Then, well, and we do not need to tell that it is excitation. It can be excitation or emission or recombination. But between valence band and conduction band, here one can add with emission or absorption of a photon. It's nothing wrong to be redundant and repeat the same information once again. So with absorption or emission of photon, then radiative transition. then it becomes almost a trivial statement, but everyone would agree. And the next one, relaxation, excited state, band H. Inside the band, here one can also add with dissipating excess of electronic energy into lattice vibrations or into phonons, called non-radiative. So same like in instruction, in teaching, it's better to say more than less. Make sense? More comments to this one? Here's my favorite. Any comments or suggestions to this figure and verbalization? Everyone is happy or not very upset?
I guess do the labels and the dot density states correspond to labels the absorption?
Well, the labels need to be relabeled. Like,
It should be opposite of each other. Or something.
well, one can use transitions, like instead of C put here from A prime to A, right? Pairs. Or design new labels, but do not repeat the same symbols, like use Greek letters or just capital Roman. Right? And what I could imagine doing, I don't know, it is maybe sort of personal taste, but okay, good. So what one could, it doesn't deal with figure and caption, but it can be brought into consistency with figure and caption. So we do have two objects, one density of states and another is spectrum, and in both we do labeling of peaks. And now we may want to establish logical connection between them. Right? So one can have like table with peaks in density of states and peak in spectrum, and then have for them like different notation and different wavelengths, different transition energy. And like from A prime to A will be maybe peak C. And then carefully go through all transitions and try to establish how they correspond to each other. Like if we are not very ambitious and do not have much time, probably we cannot go too far from like transitions between lowest 2 or 3 peaks, and it will populate this area with optical transitions. Right now we do not know whether it will help the rest of the paper, but it is kind of organizing the available knowledge. And later on it may help to understand the relaxation. Okay. More comments or suggestions to this figure?
I have some question about the band gap. So
Okay.
right now it's like 2.2 electron volts, right? So
I disagree.
yeah, if we compare the band
not,
structure,
It's not 2. It is. Well, let's ask the first author. So let me expand the question, and then Fatima may answer. So right now we do add width to each line, and this width is so broad that it cover and combine several peaks together. But there is a probability that there are a couple of peaks really at band gap, and then there is a degenerate states a little bit away. But positions of peaks definitely would give not 2.2 but something like 2.9. Just looking on this image. If you put here, if you be minus 2.4, here will be plus 0.5. 0.5 plus 2.4 will be 2.9, right?
Okay, so band gap is the energy gap between these two peaks then?
No. Energy gap is energy offset between home and loom.
Yeah.
But you may cover this question in the text, or maybe define it even in the captions to the figure, showing that there is ambiguity. There is a formal band gap from HOMA to LUMA, and there is a energy difference that corresponds to major group of orbitals in this area. Because right now, for a person who looks on it for the first time, it looks like glowing discrepancy. This one is much bigger than 2.2. And maybe, and we cannot visually subtract the scales. Maybe one can do figure with more fine resolution and showing another structure, not for here, but for supporting information, or just explaining by words. So just be aware that future reviewer may ask the same question. And there is nothing against the work. It is just a wish to have a clear picture. It's the definitions and connections of what we see.
More dispersion curve looks like 2.5.
Okay. So it's better to double check and maybe add one more significant figure. Do these images include summation over all K points?
Yeah.
Good. Another thing that I would ask as a reviewer, for one-dimensional structures, one often expects to see so-called Van Hoff singularities, or droids. So the dose for one-dimensional structures is expected to approximately show these features. So the peaks are expected to be non-symmetric, going away from together. And here we do not see it. I wouldn't say I don't care. It's fine. There can be several reasons for not seeing it, but again, a reviewer may ask it. Just giving heads up that we may to discuss it at some point, maybe not in the results section, but in the discussion section of the paper.
Your E11 transitions just limited to nanotubes, or carbon nanotubes, or is that something?
It's broader for any one-dimensional structure. Well, in each materials in each structure, there are different leading processes that determine observables, and leading process often differs. So if one goes from nanotubes to conjugated polymers, the leading process would be formation of polarons, which will kill all other things and make them negligible. And maybe here in nanowires, maybe it's not as important, but maybe it's just heavily degenerate, or it is because of the indirect band gap features. So some bands have indirect, they have minimum not at the gamma point but aside, and this may spoil expectations. But a reviewer will likely ask a question about Langhoff. Any suggestions or questions about this nice schematic diagram? Yes, in your calculations, the states are correct, but in this paper we neglect holes. So what's the reason to like the lowest state is 88? What is 88? Like some people were born in year 1988, or what's the magic number? So let's start from maybe 1, 2, 3. So it will avoid unnecessary questions. But it's a really great picture. It helps to understand how states are labeled. More suggestions, questions to this one?
I think in the text the axes are
Yeah,
referenced
they are.
backwards. I made a note of that.
What?
I think
The ones that are labeled
X
as
and
X and
Y.
Y, the text are backward.
Okay.
that's the only thing that is
Mm-hmm.
be fixed for that one.
Yes.
And what's the point of this figure?
Fatima, would you like to answer yourself, or would you like me to explain?
I can answer.
Okay.
So in this research, we combined all the orbitals for 4 different K points into one single file, combined file. I mean, we combined all the orbitals for 4 different K points into one file, and this figure shows how those orbitals are arranged in that file. The combined file.
Make sense?
Not really.
Okay.
What's the meaning of a combined file? Yeah.
Okay. Let me. Go over it once again. So when we were, some of us were practicing spin unrestricted dynamics, where each orbital has 2 projections for alpha and beta, and then the number of orbitals is double. Here, in only this specific example, number of orbitals is multiplied by 4, right? And unlike spin unrestricted, you have transitions between all orbitals. So for like LUMO plus 1, there are replicas at each K point. And there is, the following question is not scientific, it is more organizational for programming. How to label each unique state so that labels do not coincide. Because this and this will be LUMO, just with different value of K vector. And the reason of this figure is to introduce continuous numbering of all involved orbitals, so that they go in ascending order. 1, 2, 3, 4, 5, 6, 7, 8, and then it will continue further.
So this figure is just related to technical side.
Yes,
That's
technical
exactly.
side explains notation. So if you have some ideas to how to highlight it in the captions, you may mention there. Any suggestions to this figure? I'm happy with it. I don't have any objections.
And the only thing I said was just in the captions to mention that all transitions show quicker relaxation than just direct.
Mm-hmm.
Besides that, everything else is looks
So,
good.
I guess still the position of LUMO is a little bit suspicious. So at least it is not consistent with the band structure in the previous figure.
Okay. Fatima, can you know how to fix it? Just add the constant to all energies in MATLAB code so that it will coincide.
Constant means like
You understand, right?
primarily.
In the you can write it just in the script.
Oh, okay.
Energy pop equals energy pop plus whatever 0.3 or minus 0.3, so that
Okay,
you
whatever.
consistently shift all energies.
Okay.
Because here there is no here there is no reason in this absolute values. Yeah, it could be also, well, we could shift all energies so that this will be zero, then there will be no questions. But then we will, yeah, this could be a possibility. But go over it, make sure that labels are consistent in different places. This is nice work, and we do not want it to be delayed by reviewers for some notations or labeling.
So I need to add a constant so that this LUMO is going.
So if here your LUMO is 1.3, and here your LUMO is 0.5,
Okay.
then 1.3 minus 0.5 will be 0.8. Right?
Okay. So I need to.
So you need just to shift everything consistently by minus 0.8.
Ah.
And then it will remove any questions. Yeah.
And also for the bottom figure, is there any way to simplify it? Because right now it's super complicated. Is it possible to just show one key point and put other in the spot information?
Then it will be too many figures. Maybe one can do the idea that you are suggesting to dissect this figure on separate key points and provide them in supporting information. But right now, if we multiply number of figures by 4, it could be too much.
No, here just show one key point and transfer these two figures to the spot information.
Oh, well, it is a healthy idea, and if all key points would show same trends, then it would be reasonable. But there are outliers that are better represented if one can compare them. So what one can probably do is to maybe just make some additional tricks to visualize it in a better way. So if you have seen papers by Viktor Klimov or by Eric Hobby, anytime they put symbols, they make them like really huge, maybe 2 or 3 times bigger than here. If there are lines, you will see later what Aaron did to his lines. Do not do just colors, do dots and dashes so that lines really differ from each other. So make some additional effort to make it visually appealing and different.
I have an idea.
Huh?
So I think I can draw these all transitions separately and put it as inset.
That's what I was gonna say. You could probably break it in like in the 2 different figures, or like a top half and a bottom half.
I think top ones are good. Complicated ones are the bottom ones.
Well, you can try several options and put all of them into supporting information, and then we will discuss once again and put the best one in main paper and leave the rest in supporting. But with me, I would be fine with this one. Well, let's try. Maybe you design something better. One can. Well, this space is unnecessary, right? It's used only for legend. If one take this space away and maybe expand it in vertical axis to change it aspect ratio. Like right now it's 1:1. If you make it 1:2, then these lines will resolve and one can see more details. For journal, it will be not a problem to use the whole page for the figure, so that these fine things will be resolved. Okay, maybe you'll try again to represent it better, and then we'll compare, because each of us have different opinions. Okay, thank you.
I have a question about this.
Oh, okay.
That figure, the graph.
The graph or the table?
No, the graph. Okay, there was a question about normalization.
It is a really important question, but you didn't address it yet, right?
No.
Because if you address this question, it may make better science and also better representation of the figure. So upon normalization, the offset between these 2 figures will be less.
Okay, so I need to normalize relaxation times, the values of relaxation time multiplied by the difference between k point and divided by total number of k point.
Yes.
So how about then?
But again, if we do something in a quick mode, we can make things worse than better. So maybe we focus on explaining what is ready by now, and then without rush, focus on all the remaining details in the next paper. I'm very welcome if you try to fix it.
Then my question is, how about the relaxation time at
Wait.
k point?
Normalize relaxation rates and then convert normalized relaxation rates into times.
Okay, and for 0 k point, the values for 0 k point, I don't need
For
to normalize?
for direct transitions, normalization is not needed.
Okay.
Only for altogether transitions when it's normalization.
No, like my question is, there's some values for relaxation rates at 0 k point, right?
Mm-hmm.
I mean gamma point. So should I normalize then and that values also? So
What do you mean at 0 k point? When you include
There are
all pathways,
Hmm?
but your initial condition starts at 0 k point.
okay, so my 1 k point is 0, and one is 0.16, right? So at 0.16, I understand that I need to multiply by 0.16 and then divide it by 4, right?
The normalization has to be done consistently for all results computed by including both direct and indirect. it will be the same factor for all results. It will not depend on initial condition. Sure. Because on your diagram, so even if you start at 0, it doesn't mean that it will go here. It can go to different k point and then return to 0. It can go to different k point and then go down. So there are several pathways, and in order to do right normalization, one needs to divide these rates by some factor.
So what's the factor I need to?
I expect that it will be equal 16, but I do not want to make mistake, and I'm not taking it, saying it for the record.
Okay, I understand that all the relaxation.
I'm very interested in this discussion, but we need to have time for the rest of the papers today.
Okay.
How much time do you have?
It's 5:45 right now.
Okay. More questions on about orbitals. Anyone has objections or admiration of the orbitals or some constructive?
What's the point of this figure? They all look the same, right?
Right. But the transitions, like the shapes of orbitals, determine both radiative and non-radiative transitions. Right? So we need to learn how to read these orbitals. So are they composed of p-type atomic orbitals or s-time atomic orbitals? So there are several features, and like for LUMO, at different k points, you see that there is a change of shape of orbitals, and we want to bring a bit of clarity, like how to explain the things that we observe. So again, probably it is a job not of all of us, but of the first author, but we may discuss it at least to develop some brainstorming ideas. So whether it is on P composed of S or P, whether the density is localized on the silicon atom or in between, right? And if you look through, like sometimes this density covers atoms and sometimes they're completely empty.
Sometimes you get them on the surface, hydrogen.
Exactly. Then if it is on the, if you were taking chemistry, you know, there are this bonding and anti-bonding orbitals. Like occupied orbitals are assumed to have density right in between atoms, and unoccupied are assumed to have a nodal plane crossing this bond line. So another thing, whether the density is here, density goes along the bonding lines. It looks like bonding orbital and it goes along the line, and it partially covers atoms. Here it doesn't cover atoms, and it is not localized on the bonding line. It's just charge density is localized in the space between all lines and between all atoms. Well, it looks a little it induces some suspicion. I don't know if it is correct or not, but right now we have these results and we may want to describe them. Another thing, if we go further to higher orbitals, right now the density is only on silicons. Later on, there is something on hydrogens, on ligands. Another thing, if you have already read through Draft by London, you have seen that at least there were discussions. I don't remember from the top of the head. You know that one can, when we do without file, we integrate over x and y, and one can plot one-dimensional envelope function. Like if we integrate along x and y, it will be bigger density where there are atoms and less density in between them, and one can develop approximate patterns of these orbitals in projection to one dimension. So for this envelope functions, there also can be different trends. So it can be continuous, having peaks of the equal height at each atomic layer, or it could be like higher height than 0 and then another higher heights to follow the pattern of the particle in the box. Or again, not for the record, but some features can be recognized in these patterns. There is no direct protocol how to connect the shapes of orbitals with observed trends, but for some missed mechanisms, shapes of orbitals can become helpful on one hand. On another hand, a reviewer would ask for orbitals if we do not have, or would ask for explanation of their shapes if we do not provide such. So it's a reasonable thing to look over. More questions about work of Fatima? Okay, then let's collect the feedback. Which time do we need to depart? Anyone needs to depart like sharply at 6?
I mean, I gotta do stuff at some point when we're done here. It's not like it needs to happen at a time.
Are you done with reading everything? Who wants to persecute or advocate for Aaron? Then I will complete my reading so that.
Yourself?
Yeah, I guess.
But you cannot be too critical to yourself. Well, probably you can, but it is not in human nature.
Are these the ones that you printed off, or the ones on the
Yeah.
updated? Well, I guess I'll just go up there and bring it up.
Computer?
So any problems with the layout of this figure? Nothing?
I got nothing.
No, I'll probably postpone reading yours to later, and I will with the discussion then, because I have tons of comments. It is not nothing. It's a lot. So right now you can see and practice both criticizing each other and learning from each other. So and you guys are really show some strong thoughts and strong skills in one aspect by one person and another aspect by another person. So there could be real benefits from labeling peaks in the density of states, not just some labeling, but physical labeling based on your exposure to particle in the box model, a three-dimensional box, and also based on the community effort. If in quantum dot community where most of the boxes were not three-dimensional boxes but spherical boxes, where there are each wave function is product of atomic wave functions times envelope, right? And envelope wave function in a spherical container follows like separation of variables for angular momentum and radial part, angular part and radial, and therefore it shows same progression of eigenstates with different values of angular momentum, like S, P, D. By analog to this SPD, one can also look on the one-dimensional box, seeing like if it is lowest available state. Again, we have two progressions, one for electrons and another for holes. Right? And for instead of S, it is just lowest state. Instead of P, it means it is excitation either in X, Y, or Z direction with one node. D will be either two excitations in different directions or double excitation in one direction. Like in the box, there is a state 1, state 0, 1, and 2, or 1, 2, and 3.
Maybe a single optical transition, which is
No. Just states inside one band. First, second, third. Associate peaks with progression of state of the envelope function in the due to confinement in a box. So it will be nothing wrong, and it would be very reasonable connection to community if one can call them like peaks here, SPD for electrons and SPD for hole, right? And then one can associate each of the peaks in the computed absorption spectrum by transitions between the peaks in the density of states, same as in work of Fatima. Again, not individual transitions because many of them are degenerate, but leading group of orbitals. One leading group of orbitals to another leading group of orbitals. And if one would, I was just sitting and playing with calculator, trying to subtract these numbers and see which transitions they generate. So the first 4 peaks could be summarized in the same way as you can put a table for peaks in density of states and peaks in spectra, and those could be like S to S, the lowest one, S to P, P to S, and then P to P. And it works really well if one looks through the numbers. So it doesn't change. It doesn't provide any change to figures, but it gives some meat in interpretation, what one can see. And this will be especially attracting the experimental community. So it is something that one can pick from basic models without any derivations, just general idea of progression of this envelope functions due to quantization for electrons and holes and transition between them. You do not need to put equations and calculations for boxes. Just declare this, that it looks like this principle is followed in these calculations. Also, one can expand this table for more columns and put leading pairs of orbitals, that most representative pairs of orbitals for each group. Later on, it can be used for selecting the initial excitation and following the pathway of the fully excited electron dynamics. Dashes are experiment, right?
Yes. I think I put that
Yes, you did. For which size?
for the ensemble.
Okay, ensemble with which average diameter of whatever. So, at least, what's the ratio of the dot in the model and the size of the dot in the experimental?
I like 10.
Okay.
Oh, hi.
Well, you do not want to brag about it, but it is like a glowing thing. If we need to find a way how to explain transition.
And also, if you want to make such a comparison, do you need to mention the ligands of the
Right.
Right.
Did you mention it in your?
Yeah.
You did?
Yes.
Okay, thank you. So that experimental ligands have much longer hydrocarbon chains. Okay. Were you planning to add EDOS as a third line?
In the SIs somewhere. I was digging through some of my old figures and figured.
Because it could be really helpful in the interpretation. So the first time I looked on this figure, I didn't realize that it is experiment. I thought this line is EDOS because it is expected to be about this shape. So the EDOS is expected to have much higher density in this region, right?
Mhm.
But they are the transitions S to P and P to S are expected to be dark, although there are abundance of them.
Your
And it
call
is
will be
also-
disconnected.
It's not super novel, but it is interesting observation, and it shows that we are on the right track. So if you add, if you consider to add this image, this line to the figure, it can be beneficial.
Overlay it with in that C figure
Yes. Yes.
to like the approximate scale,
Mm-hmm.
like match the highest peaks.
Well, if you do EDOS, you do not need to adjust anything. In the EDOS, you practice the same equation as you did for spectra, but you remove the oscillator strengths. Right? So it is oscillator strength for most of transitions, it is 0, right? There are very few bright transitions. Therefore, EDOS generally will have peaks at the same place, but they will be higher.
I have another question about the spectrum. So if we look at the feature C and feature B, it seems the simulated observed spectrum has a blue shift, right? So in this case, I guess maybe feature A is an artifact.
So in the intuitive expectations, the computed spectrum should be blue shifted
Yes.
all peaks, and experimental spectrum should be redshifted for all. We cannot say that feature, well, comparison between experiment and this calculation is yet tricky. It is we can leave the figure this way, but we need to put a lot of explanations and discussions. It is not ready yet to go. I wouldn't agree that feature A without prime compute is an artifact. It looks, at least from what I see and what Aaron is explaining, as very reliable. So it is the Homo orbital looks as it is expected. So it's localized on bromines, and it is only those bromines that are not on the surface but in the center, in the core of this structure. So it is situation with unoccupied is not as so they're not shown because they are degenerate, and they are because they degenerate, and because they are sometimes protrude to the surface. I don't know how it will look like upon doing true excited state with excitonic binding energy, but in this work we are far from it. Okay. Any criticism or suggestions in here? I'm fine with everything except the word modulates. We can make a brainstorming, or maybe Aaron can do a brainstorming session with himself. I would say something like Redfield summarizes intensity or represents electron phonon couplings. Modulates is a little too narrow. But it's just semantics.
Mm-hmm. So, in panel D, why the intraband transition is not observed in the other figure? In the white band?
I do have an answer, but it would be really interesting to hear what Aaron would.
I mean, in the time integrated?
Yeah.
It's just because it accumulates so many counts that it's probably like 4 or 5 orders of magnitude higher.
Okay.
So it's there. It's just you can't see it.
Like here, it part of the trajectory from 1 to 100 femtoseconds, and here is from 1 picosecond to 1 nanosecond. So it is like several orders of magnitude larger number of counts. And if it is a like experimental detector, if it is a million times more counts, it will be sure much more visible than this one. More objections? When needs to design title? If anyone has an idea, please suggest. So just looking at what is compared to what, or what is most surprising good or bad. It's nothing wrong to point attention on something. Why 10 times difference in size give the same spectrum? Well, there are. It is forbidden to have reviewers from the same school, but I know which question Professor Krzyzewski would ask if he would be a reviewer of this figure. He doesn't. In the discussions, he still doesn't want to believe, and he wants. Like one day he says okay, next day he comes up with this question again. So if it is for 300 Kelvin, which is like 0.03 of electron volt, why the amplitude here is like 0.5 electron volt? Just develop your own answer. It's not one minute discussion. There is nothing wrong with calculations. It is a response of electronic structure to thermal motion of nuclei. It doesn't need to be equal to size of phonon quantum. But try to think and formulate your question. Any more questions to this one? Any objections to this summary of trends?
For the green one and the red one, it seems we have two outliers. What's the nature of this transition?
What do you mean by nature?
Why there are outliers?
Oh, you mean like why
Right.
this one
Right.
is so far off and why this one is so far off?
I think it's because it's the LUMO plus one or HOMO minus one to HOMO, and it only has one possible transition. It seems. Well, that's the only thing I can correlate between them, but I don't really understand why. Like for those 2 points, they deviate from the rest of them. But
So there is no big hectic entourage, but you may do not postpone it and maybe include your vision and explanation just in the caption of the figure. Because who knows, will be there time to discuss it in details in the main paper, and now you are looking on it, and maybe this evening you will be going through comments. We may add some thoughts in response of this question just in the caption.
so the green one and the say red one or black one?
Red one?
Red one. So for the whole states, there's usually between HOMO minus one and HOMO, there's a decent sized subgap. So that might explain why if you just populate HOMO minus one initially, that it deviates from the rest of the trends.
Okay.
But the green one, it's like there's not a subcap, so I guess I don't know. We could just say it's not the right basis to describe electrons, since they're strong spin orbit coupled.
Well, it can be not the shortcoming of the methodology, it can be objective property. Some physical reason. Due to spin orbit, there is a bigger, when you switch it on, there is a larger, no, it is without spin orbit.
Yeah, and there should be like zero sub.
Well, I'm more interested why all these three lines start at after point one, and this protrudes to here. Is it?
And that's due to not having spin orbit or no subcap.
Okay.
Because the hole always has a subcap, and then when you do spin orbit with the electron, that produces a large subcap. But the electron without spin orbit, there is none. I think I put that in the caption when I wrote it this morning.
Okay. So what I would suggest to do is to feed it very, very roughly by single line. So there are many reasons to deviate from a single line, but it's the simplest thing, and one can discuss general trend. And then one can immediately draw conclusions. So for holes, presence of spin orbit keeps the same trend. So the relaxation time increases with increase of energy, so it is matches gap law, right? And by the way, the average offset between these two lines can be treated in the same way as Fatima has done it. After all the figures in the main paper, she has a table where she gives like energy. Well, in her case, it is not Wiesent without spin orbit. It is Wiesent without indirect transitions. But she has two, or more than two, data lines, data sets, and she summarizes how subtraction of them behaves like a constant, or maybe also like a linear function. And she did it because number of data is indeed very large, and if one would discuss each data point, it would be a kilo. And if one just like, there are average trends and there is a difference between them. But for holes we are fine, but for electrons, just qualitative trend changes. So it goes from expectations along gap law to opposite. And typically it happens when density of states substantially increases. When there are several, like gap law goes when it is subsequent transitions between states that are offset from each other by energy, and opposite trend is when there are dense states and one can go in parallel pathways. But putting this discussion right below the figure could be a good idea, because later on one may need to, if there are intentions to make it a letter, there could be no space for all details. And when there are explanations here and there, then one can shop and select the best things to main text. More questions to this one? Anything about the images? So I'm happy with the images. But you may also verbally describe what is observed, and also if time allows, you may try to rerun this movie, construct it yourself independent once again to see that all the same trends are observed. So generally it looks right, but I see a couple of things that may be signs of something wrong, or they're seen just because this image has much higher, finer resolution. So the blue area must correspond at the very last step of the relaxation, must correspond to the HOMO orbital, right?
Mm-hmm.
And
that should be S-centered in the middle?
Yes, yes. And instead, one does see something on the corner, which contradicts the this image. It shows nothing on corners.
Yeah. That ISO value anyway?
Yes, it is ISO value, and ISO value are low resolution, and this figure is much higher resolution. But
It does look pretty dense though.
huh?
Like from the figure anyway, it looks just darker, the colors are more intense. Right?
Also, well, there is a substantial density on this carboxylic group, but it could be fine. This,
There should be some on all.
yeah, the HOMO orbital also shows some density on carboxylic groups. But before we come into hectic mode, probably it could be reasonable to double check. Just maybe rerun once again, make sure that if there are errors, I want to believe there are no errors, but the first one to check if the count of orbitals is missed, and what we count as HOMO is indeed like maybe HOMO minus 1, and all count of orbital could be shifted. I would double check for this error. Okay. Anyone wants to advocate for London? Or we are already tired for today? Probably, let me suggest that we agreed to meet for like 2 hours, and it is somewhat more. So let's conclude for today, and I promise to provide details, comments no later than midnight, and we just collect whatever was developed by Fatima.
Extend into Friday.
Huh?
Extend into Friday.
I won't be here on Friday.
Oh.
I gotta work at the Emporium through meetings.
Okay, so can we declare the meeting completed? Where's the camera? Meeting is done. Yeah, thank you much for contributing, and I think it will really benefit completion of this.